What's up, y'all? In today's video, I'm going to be going over how to tackle these combined spec problems. So when you first see a combined spec problem, it might be very overwhelming with all the different pieces of information they give, but there is a certain formula and pathway that I like to follow every single time to find the correct structure of a molecule. Let's go over those steps right now. Okay, so the first step is to find the molecular formula of the compound. This can either be given or it can be more disguised. It can be given as a mass to charge ratio. It can be given in a mass spec, and you have to find the molecular weight of the compound. So I would always start here first. Find a molecular weight, and therefore a molecular formula. Now, the next step is to find the degrees of unsaturation of that molecular formula. So how exactly do you find the degrees of unsaturation? It's going to be this formula right here. Be sure to memorize it. And it's also important to know how to apply this number. You're going to get a degrees of unsaturation of a whole number. And basically what that is going to tell you is however many ring structures or pi bonds are present in your molecule. So now at this point you should have a molecular formula and you should have a degrees of unsaturation, which should tell you what your structure should generally look like. Alright, now that you have all that, it's time to now that you finally have those pieces of information, let's start by looking at the IR spectra. So it's important to know that the IR spectra doesn't exactly tell you what the molecule looks like. It only tells you what the machine senses is present as a functional group. For example, the most important functional groups that commonly come up are the alcohol group at 3300, the carbonyl group at around 1720, and the C single bond O group around maybe 1100 or 1200. In addition to functional groups, other things that are important to look for are overtones, out-of-plane bending, as well as a signal to the left of 3000, because that indicates you have sp2 hybridized carbons and therefore probably an aromatic benzene somewhere in your molecule. Alright, now going on from here, now we can take a look at the proton NMR, which in my opinion is one of the most helpful pieces of information to help you find the structure. And what you guys want to do is make an integration table, as you'll see in the problem I will do later on in this video. That really tells you in a very ordered, methodical way how to approach the proton NMR structure. And after you look at the proton NMR, then I would look at the carbon NMR. In my opinion, the carbon NMR doesn't really tell you as much as the proton NMR, but it does tell you a pretty important piece of information in that wherever you see a peak on the carbon NMR, you want to see if that peak matches the number of carbons within your molecular formula. So for example, let's say your molecular formula has 8 carbons, but your peak only shows maybe 5 or 4 peaks on the carbon NMR. Because there are fewer peaks than there are carbons in the molecular formula, it is likely that there is a plane of symmetry somewhere in your molecule. Even though there are, for example, 8 carbons in your molecular formula, the machine can only detect certain, like let's say 4 or 5 carbons because some of them are chemically equivalent. Right, once you have all of that information, then you can propose a preliminary structure. Basically, we went over this in class, indicate whether each proposed structure is an end piece or a mid piece, and try fitting them all together. There are only a certain number of ways these pieces can be fit together, and if it might be kind of confusing, that's where the next step comes in, which is spin-spin coupling. This basically tells you the protons and their chemical surroundings, basically their neighboring carbons, hydrogens, however many present they are, tells you how many peaks, whether it be a doublet or triplet, a quartet, or an M, whatever integer higher than 4. And that is also going to be present on your proton NMR. Now that once you've done all those steps, it is very likely that you've reached the correct structure. Now let's get into a practice problem. For combined spec and all these kind of spectra problems, you can't just memorize like you can with reactions and how the reactions go, ortho, para, meta, that kind of stuff. It is very important to know how to apply the knowledge that you guys know into solving problems. You can't just memorize this or study within a day. There's only so many ways in which molecules can appear on these spectra because atoms and molecules can only be arranged a certain number of ways. So once you understand the methodology and pattern to finding these structures, then you can pretty much deduce most structures given a combined spec problem. Alright, so we're going to look at this question here. Compound 4 has a molecular formula of C10H14O and falling IR and NMR spectra. So the first thing to always do is to find a molecular formula, and thankfully this question gives it to us. Right here we can highlight it, and the first thing is to get the molecular formula, and once we have that we can find the degrees of unsaturation. So the degrees of unsaturation formula is going to go the number of carbons, 10, minus half the number of hydrogens, plus 1. Remember, we don't want to account for oxygen here. We only want to account for nitrogens and halogens if they should arise. So this should give us degrees of unsaturation of, if we do the math out, it gives us 4. And then it asks us, is compound 4 aromatic? And whenever we see degrees of unsaturation of 4, we can assume that it is. Very likely to be aromatic. And when we have aromatics, we're dealing with benzenes. So remember, it's going to be this one ring here that accounts for one of the degrees of unsaturation, and then the 3 double bonds, which accounts for the remaining 3, for a total of 4. Then it asks us, what is the frequencies of the out-of-plane bending? Remember, that is going to be relevant in the IR spectra. So given the IR spectra, the out-of-plane bending is going to occur on the right side of the spectra, and this one is going to occur at 827. So now the question is going to ask us for any equivalent carbons, and I'm going to skip that for now and go to the next one down. What is the functional group here? So when we look at the IR spectra, let's look at what initially jumps out to us. When we look at the spectra, what jumps out to me immediately, and hopefully to you guys as well, is this big alcohol stretch, this OH stretch here. And whenever we have an alcohol stretch, we want to also look for a C double bond O stretch, because with alcohols, they can occur just by themselves, or they can occur as a part of carboxylic acids like this. We want to account for the C double bond O group, and that occurs at around 1720. And if we look here at 1720, we don't see anything. No massive peak. So there's no C double bond O group, so we can probably assume that the functional group here is the alcohol. Okay, so the next step is to make an integration table and look at our proton NMR. So let's go from left to right here. We have an integration. Let's say we have around, what is this, 1.4 with an integration of 9 hydrogens. A peak at around let's call that 4.9 with 1 hydrogen. And 2 peaks of equivalence at around 7. And whenever we see peaks around 7, we're likely to assume that to be part of the aromatics. Remember, we established that there's a benzene in the structure somewhere, so those protons are going to be part of the benzene. And I'm just going to call that a range from 6.9 to 7.2. And we're going to just draw this as 4 hydrogens, or the same thing as the hydrogens part of the benzene. So good, we already have that all checked out. And one thing to note here within this structure of the aromatic hydrogens is that this is one of the complex splitting patterns we went over. This is the doublet of doublets. It is important to understand the concepts behind this and how to identify the diastereotopic protons that contribute to such complex splitting patterns, but you won't be expected to predict if a complex splitting pattern occurs or how to solve any spectra relating to this. We can solve this without knowing too much about this complex splitting pattern here, but it is something to know of, and it's something that is very important. So now let's take a pause here. Let's add up all of our protons. Right here, I'm counting a total of 14 protons. And if we look at our original structure, surely enough, up here, C10H14O, there's 14 protons. So we know we're good on that, and we don't need to multiply anything by a factor. So the next step here is to propose reasonable structures here for our protons. So for the 9 hydrogens, most of the times, if not all of the times, whenever you see this, it's going to immediately jump out to you that this is going to be a tert-butyl group, because all of these hydrogens are going to be chemically equivalent. And for this 1H group, you might assume that it could be something like this, with a CH and then 3 bonds coming off of it. But remember, we have an alcohol here somewhere in our molecule, and that is likely going to be an alcohol here. And let's say if you did draw it with just a CH and 3 bonds coming off of that, you'll quickly find out that that does not add up to the correct molecular formula that we established above as C10H14O. So now we're given these things, these structures, and we want to say whether they are mid pieces or end pieces. So given the first torpedo group, we know for a fact that this is always going to be an end piece. It cannot go in the middle anywhere. The alcohol group, that can only be, I guess, an end piece. You can't really put that in the middle of anything. And the benzene is going to be a mid piece. We're going to be working off of this benzene. So now we have these structures here, and we can try to assemble them together. So I would say the first thing we always want to do is place down a benzene somewhere, because likely all the branches are going to be coming off the benzene. So now we have this torpedo group and this alcohol group, and we might be kind of confused of where to go from here. And I would recommend looking at the IR spectra and notice that there is a very sharp peak at particularly 827. And you'll be given this chart on the exam, but it is important to know that this is a clear example of para substitution. So we know that these two groups are going to be para from one another. So let's put that on right here. And the alcohol down here. So now we have a preliminary structure, and let's go back and check this question here that we haven't answered. Does the molecule contain any equivalent carbons? So this can be kind of looked at once we have a structure, and then once we look at our proton NMR. If we look at our proton NMR and count the number of peaks, we have 1, 2, 3, 4, 5, 6. We have 6 peaks, and if we compare that to the number of carbons in our molecule, 10 carbons, that's going to be less. So we have 6 peaks for 10 carbons. So whenever you see something like this where there's fewer peaks than the number of carbons in your formula, that is a very clear indication of a plane of symmetry, POS. And that basically means that the machine, the carbon NMR machine, is detecting 2 carbons as being chemically equivalent, so it's only registering them as 1 peak. Okay, so surely enough, in our molecule, right down the center, we have a plane of symmetry, so we know everything makes sense. So now we just want to make sure, I'm going to write this here, does this have any equivalent carbons? Yes. Okay, so now we want to make sure, using the spin-spin coupling method, or the N+1 rule, whether everything here makes sense of where they should go. So down here at the integration table, I'm going to give each of these a label as A, B, and C, and I'm going to go ahead and label that to their corresponding peaks on the proton NMR. This is going to be A, this blip here is going to be B, and for this benzene portion, remember that we kind of combined the fact that there are 4 hydrogens that are giving the signal of this benzene, but there are 2 peaks here, so I'm going to label this as C and D, and we don't necessarily know in our structure whether these hydrogens up here are C, or these ones are C, and which one is D, and which one is D. Let's say we don't necessarily know which one those are going to be. There's a plane of symmetry down here. I'm going to redraw that. And a good way to tell which one is which is how far shifted the peak appears on the proton NMR. So remember that the carbons down here, these 2 hydrogens, they're going to be chemically equivalent, and we're going to call that D, just how we called it here as D. And that makes sense because it is closer to the electronegative atom of this oxygen right here. And because it is closer to that electronegative atom, it is going to show up closer downfield at around 7.3, while the C carbons are going to show up further upfield. So now we have the structures here. We have C, we have the D carbons, we have the C hydrogens and the D hydrogens. I'll label this as C and D. We have the B hydrogen on the alcohol, and we have all of these carbons up here. I'm going to label as the A hydrogens. They're going to be equivalent. So now we're going to look for the spin-spin coupling. Let's look at A first. A shows a singlet. According to the N+1 rule, that means that the hydrogens that are relevant for A should be next to a carbon with 1 less than the number of peaks. So it should have 0 hydrogens next door. And surely enough, if we look at all of these hydrogens next door, they're looking at a carbon with 0 hydrogens. which gives a singlet peak. So that makes sense. Now let's look at B. B here is going to have a small little blip, a small little singlet peak, and that is always going to be relevant for alcohols. And the reasoning behind this is because alcohols are very electronegative, and that blocks all the effects from its neighbors. So the protons can't really see the neighbors of anything else because there's that oxygen there blocking the way. So that kind of makes sense. Once you do enough of these problems, you're going to notice that this kind of trend is going to appear in other structures with alcohols, and that is just going to come with practice. And let's look at C and D now. Let's look at C first. C is showing a doublet. So if we look at C, the carbons should be attached to another carbon with only one hydrogen. And surely enough, if we look down here, these carbons only have one hydrogen attached to them. The same thing goes with D. They have a doublet pair, and if we look up, they should be attached to its neighbors with only one hydrogen. And if we go up here, they have one hydrogen coming off of it. So that's how we know that this is going to be our final structure for the spectrum.